At what speed v will the car neither slide up nor slide down this bank turn? What is the first thing you do in any Newton's second law problem? Free body diagram. Can somebody offer me one of the forces that you will put on this free body diagram? The normal force. Can everybody point in the direction of the normal force? Go ahead and point in the direction of the normal force. Normal means perpendicular, and that means perpendicular to the surface. So I'm going to draw the normal force up like this. Now you can label it F sub n. I like to label it n, which most university textbooks will label it like that. Get rid of that dotted line. Okay, so there's our normal force. What is another force acting on this thing? Force of gravity. Now, if you label your force of gravity, and you should generally, it's a good idea to have that coming off the center of mass of the thing. If you label it mg, you are solving two problems at once. Why? Because mg is an acceptable label for the force of gravity that you'll get credit for labeling it correct, and you also have the magnitude. So you've solved two problems at once. In fact, you might have gotten 2 points at once. So, are there any, I've indicated no friction here, are there any other forces acting on this car? Any other forces? It's going in a circle, the center is right over here. Are there any other forces? No friction. So the centripetal force. You guys, why is this the biggest mistake you could ever make? No, no, no. And it's a common mistake, so I understand if you'd make it. That is not right. There is no such thing as that force. That is not a force. Do not ever, unless you want to fail an exam, never put that on any free body diagram. Why? Why is that never going to go ever, ever, ever on any free body diagram? It's, well, besides not being a real force, what do we mean when we say the centripetal force? It's the net force that points towards the center. There's no separate force that comes from outer space called the centripetal force, and it's magical, and we don't know what causes it. It just makes things go in circles. That is not the case. The question in every single circular motion problem is, what is providing the net radial force, which we call, the net radial force is simply called the centripetal force. I like to call it the net centripetal force because that's what it is. It's just the net. It's the sum of the forces that point radially that keep this thing going in a circle. What, in this case, is providing the centripetal force? Give you a hint. The center is right over here. You're trying to go in a circle around that point, and I heard someone say it. It is the normal force that's providing the centripetal force. How do we know that mg cannot be providing the centripetal force? Towards this center right there is the direction of the net centripetal force. mg has no component that way. So, you know, and what I really should have done at the beginning here, but you wouldn't know to do this ahead of time unless you had done this problem before, is to set up a coordinate axes. Usually in inclined plane problems, you want to set up your coordinate axes like this, and that's the first thing I recommend you do. X, Y, don't write this down because this is not correct. In this problem, you can't set up your axes like that because this is actually a circular motion problem where we actually have to set up our axis. One of the axes got to be parallel to the radial direction. So you got to set up your axis like this, X, Y. And only through experience would you know that. And the reason that is because we want to always split our components to a radial direction, which in this case would be parallel to X, and a tangential direction, which in this case actually would go into the page. So here's what we're going to do. Because we have to set up our coordinate axes like this, the only force that I actually have to split into components is which one? Notice that gravity is already split into components. It's already 100% y direction. Only the normal force is in two directions, x and y. So I've got to split the normal force into components. When you do this, make sure, I like to use dotted lines for my components, make sure that you put arrows on them. If your normal force is going up and to the left, your components will go up and to the left. Make sure you put arrows on those. The next thing we got to do, so for like doing problems, it's okay to put your free body, your components right in the free body diagram. That's okay. On the test, my test, AP test, it'll say draw a separate diagram with the components because they don't want to have to guess if you understand that mg sine theta or mg cosine theta or whatever it is not an extra force. Okay, so now the next question is, here's theta that I'm giving you right here. There's theta. Which angle in this triangle is theta? I'm going to give you a couple of choices. Let's make this angle 1 over here, angle 2 right there, and angle 3 right there. 1, 2, or 3, which of those do you believe is angle theta? Okay, so let's go through the process by which you must figure this out every time. Angles will be congruent if the rays of angle 1 are parallel to the rays of angle 2, or if the rays of angle 1 are perpendicular to the rays of angle 2. So here's what we're going to do. I'm going to grab a red pen here, and I'm going to mark this side of theta with a red mark right there. And I'm going to mark the other side of theta with a green mark. What I'll do is I'm going to mark these so we can talk about them. I'm going to call this n sub. What would be a great subscript for this component? N sub x. How about this one? N sub y. So now that we've identified those components, is there anything parallel or perpendicular to the green one? Okay, you might say, oh, n sub x is parallel to this one. And that would be right, except then what we have to do is find another ray parallel to the red one. Do you see another ray parallel to the red one? Anybody see a ray parallel to the red one in this triangle with the normal force? There isn't one. So that cannot be our right solution. So let's go back. Here's the green line. Does anybody see a line perpendicular with the green line? Which one is perpendicular to this green line? Somebody said it. It is n sub y. So what I'm going to do is I am going to take this green line and then take this one. This is the one that's perpendicular to that. And now we got to look for, is there any one that is perpendicular to the red line? N is. So you see why most people actually got this wrong, because you didn't follow this specific process. Okay? So it turns out that angle 3 right up here, that is angle theta. I'm going to erase these and label that with angle theta. And that's the process you're going to have to use to find theta. And there's no generalization that, the top angle is always theta. It just doesn't work that way. On the AP exam, one thing is guaranteed. You're going to see problems you have never seen before, ever. So you have to understand how to solve this generalized type of problem. And the way you do it is I like to use different colors. If you have different colors, that'll work. Do the same process we just did. Look for parallels or perpendiculars. All right, so we now have theta. Okay, we got our free body diagram. We got our components. The next part that you should always do is split the problem into what? What's the most important split you can probably do? X and Y. So what I'm going to do is I'm going to write X over here, and I'm going to write Y over here. We're splitting the problem into its components. Okay, so now you wouldn't know which one to do first. Doesn't matter which one you do first, but because I've done this problem a bunch of times, I'm going to just go with the Y side first. So what you always do is you simply write this. Start off with net force Y equals MAY. Now, why do you do that? It's because you can often get a point just for writing that. If you write out the next step with skipping that and you get the next step wrong, you do not get the point for writing Newton's second law. So if you made a mistake in your second version of that, you don't get the point. Always write that, and that gets you the point for where the rubric says the student recognizes that the use of Newton's second law is necessary. The next thing you do is you get more specific. So what are the forces that are acting in the y direction? You have to look at your coordinate system and figure out what those are and what direction they go. Now, you can In the y direction, you can pick any direction for positive that you want. I would always pick, if there's any acceleration, always pick the direction of acceleration as positive, because if you don't, you have to add a negative a to all of your a's. So the net force in the y direction, you substitute, more specifically, n sub y is positive minus mg equals may. Here's my question to you. Has anyone ever seen a truck or car going around a bank turn suddenly accelerate upward and go into space? And we're assuming no space aliens are trying to abscond with the truck or fall through a sinkhole down that way, accelerating down. Anybody ever see that happen? So, not yet at least. So that means that what in this equation can I just say, oh, that's zero? The acceleration is zero, okay? So because it's not accelerating up or down this way, I can just say, oh, that's zero. So this whole side is going to be zero. Okay, so I can say, here's n, ny is going to be n times cosine of theta. So I can write this. This is just the normal force times cosine of theta minus mg equals 0. And that tells me that n cosine theta equals mg. I just added mg to both sides. And finally, it tells me that the normal force is mg over cosine theta. Notice that the normal force is not mg cosine theta. It's mg over cosine theta. So notice that this normal force is larger than it was if this car was at rest. Why is that? Because the normal force not only has to resist against the force of gravity, the normal force is providing what force? The centripetal net force. It's providing that. There's no separate force, the centripetal force. It's always provided by something. I have just found the normal force. These are all known. Cool. Now at least I know that, now I can go to the x side of things. What's the first thing I'm going to write down to guarantee I get that point on the x side? Net force sub x equals max. And notice the subscripts have to agree. In this case, it just happens to be true that the x direction could also be called the what direction? You can't make it the negative direction unless you want to make sure you add a negative a every time you have the letter a. Hint, here's the center of your circle right here. X direction to the left is going to be towards the, which we call centripetal. So I'm just going to rewrite this as net force C equals MAC. And whenever you do that, you can always write net force C equals mv squared over r. Now here's my question to you. Is that equation true if the object is changing speed? Whatever your speed is at that instant, if you're going through a circle of radius r, the net centripetal force must be mv squared over r at that instant. Yes, the net force centripetal can change. If you speed up, you got to exert more force to keep them in that radius of circle, but that is true always. The centripetal component will be mv squared over r. Sweet. Okay, now let's get more specific than just FC. What can I put in to get more specific for my next step? What is providing that net centripetal force? N sub x. It's this one. This is the only force. Notice that we have no friction in this problem. This is the only force pointing towards the center of the circle. Should I make this force N sub x positive, thumb up, or negative, thumb down? It's pointing to the left. Should I make it positive or negative? Why is that always going to be positive? It's the direction of acceleration. So that's going to be positive. So that is going to be N sub x, that's my only force, equals mv squared over r. Okay, now let's get even more specific. How could I rewrite N sub x? N sine of theta equals mv squared over r. Now, what am I actually trying to find in this problem? V. I'm trying to find V. So here are my two equations. What's one simple way to solve two equations? or to combine them. You can substitute. What am I going to substitute into this equation here? Aha, see, I've got the normal force right here. I want to substitute that in for this n over here. So again, you get even more specific. For n, I'm going to write mg over cosine theta, that's n, times sine of theta equals mv squared over r. And this is another example of why you never want to plug in any numbers until the very last minute. You're going to be crunched for time on this exam. That's one thing I can guarantee you. So you don't want to spend time when you don't need to. What did we not even have to consider in this problem? Mass cancels out. So if you had gone and multiplied the mass in your calculator, clickety-clackety, clickety-clack, you are wasting your time. Solve everything symbolically, and only at the very last minute would you actually have to plug in any numbers. Sine theta over cosine theta is better known as what? Tangent of theta. G tan theta equals v squared over r. So all you got to do now is go ahead and you solve for our unknown v, and you get gr tan theta, and then to get rid of that, you just do the square root. That's the v that we're looking for.